Welcome to Dark Cosmos Theory. Before we begin, I want to ask you something. Where are you watching this from? Drop your location in the comments. It's always incredible to see how far across the world our cosmic community reaches. And if you enjoy content like this, please hit that subscribe button and turn on notifications. It really helps us continue bringing you the mysteries of the universe. Now, let's drop your comment and dive into something that will fundamentally change how you think about reality itself. Everything you've ever seen, every galaxy ever detected, every star that's ever caught your eye through a telescope exists inside a sphere only 46 billion light-years wide. But scientists now believe there's something on the other side, something we were never meant to see, something that might be larger, stranger, and more powerful than anything inside our cosmic bubble. And the evidence for it is hiding in plain sight, written in the oldest light in the universe, carved into the fabric of space itself. Stand outside on a clear night and look up at the stars. What you're seeing is the observable universe, the portion of reality that light has had time to reach us from since the beginning of time. But here's what keeps cosmologists awake at night. The observable universe is not the same as the actual universe. It's just the part we can see. The cosmic horizon that defines the edge of our view isn't a wall, it's a limitation. A boundary imposed not by space itself, but by the nature of light and the age of the cosmos. And beyond that horizon, something exists. The question that's tearing through the foundations of modern physics is simple yet terrifying. What's out there? For most of human history, we believed we could see everything that exists. Ancient astronomers thought the stars were fixed to a celestial sphere just beyond the planets. When telescopes revealed distant galaxies, we expanded our cosmic view but still assumed everything that exists was, in principle, visible. Then came the 20th century, and with it a realization that shook the very foundation of cosmology. The universe has an edge, not in space, but in time. And that edge creates a horizon beyond which we cannot see, no matter how powerful our telescopes become. The story of this cosmic limit begins in the 1920 seconds, when Edwin Hubble made a discovery that would change everything. Using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble observed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. This wasn't just motion through space. Space itself was expanding, stretching like the surface of a balloon being inflated, carrying galaxies along with it. The implications were staggering. If the universe is expanding now, that means it was smaller in the past. Wind the clock back far enough, and you arrive at a moment when all of space was compressed into an infinitely hot, infinitely dense point. The Big Bang. This wasn't an explosion in space, it was an explosion of space itself, the moment when time and distance and matter all began. But here's where things get strange. The Big Bang happened approximately 13.8 billion years ago. You might think that means we can see 13.8 billion light-years in every direction, giving us a sphere with a radius of 13.8 billion light-years. But the universe doesn't work that way. While light from distant objects has been traveling toward us for billions of years, space itself has been expanding the entire time. The objects that emitted the light we're seeing today are no longer where they were when they released those photons. They've been carried away by the expansion of space. When we look at the most distant galaxies Webb can detect, we're seeing light that's been traveling for over 13 billion years. But those galaxies aren't 13 billion light-years away anymore. Due to cosmic expansion, they're now roughly 46 billion light-years away. This creates our observable universe, a sphere roughly 93 billion light-years in diameter, with Earth at the center. Not because we're special, but because that's how observation works. Wherever you are in the universe, you're at the center of your own observable bubble. This cosmic horizon is fundamentally different from any other boundary in nature. It's not a wall you could reach by traveling far enough. It's a limitation imposed by the finite speed of light and the finite age of the universe. Light from regions beyond this boundary simply hasn't had enough time to reach us yet. And because of cosmic expansion, some regions are receding so fast that their light will never reach us, no matter how long we wait. Think about what that means for a moment. There are entire regions of space, potentially containing trillions of galaxies, billions of stars, countless worlds that are and always will be completely invisible to us. Not because they're too faint or too far away for our current technology, but because the structure of space-time itself prevents their light from ever crossing into our observable bubble. The cosmic horizon moves outward as time passes, but only slowly. Each year, light from regions roughly 1 light-year beyond our current horizon has time to reach us. You might think this means we'll eventually see everything, given enough time. But the accelerating expansion of the universe complicates this picture dramatically. In 1998, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe isn't just continuing, it's speeding up. Galaxies aren't just moving apart, they're moving apart faster and faster with each passing moment. The force driving this acceleration is something we call dark energy, though that name is really just a confession of ignorance. We don't know what dark energy is. We just know it's there, making up roughly 68% of everything that exists, pushing space itself apart at an accelerating rate. Dark energy changes everything about the cosmic horizon. As the expansion accelerates, distant regions of space are being pushed away from us faster than light can travel toward us. This creates a boundary called the cosmological event horizon. Anything beyond this boundary is not just currently invisible to us. It will remain forever invisible because light from those regions will never be able to catch up to us against the accelerating expansion of space. The cosmological event horizon is currently estimated to be about 16 billion light-years away. That's the distance beyond which galaxies are receding faster than light. Light from those galaxies is still traveling toward us, but it's fighting a losing battle against the expansion of space itself, like a swimmer caught in a current faster than they can swim. Every photon is moving toward us at light speed, but the space between us and those distant galaxies is expanding faster than the photons can cross it. This means there are galaxies we can see today that we won't be able to see in the distant future. As cosmic expansion accelerates, more and more of the observable universe will slip beyond our cosmological event horizon, their light stretched to wavelengths so long they become effectively invisible. In the far future, trillions of years from now, observers in our galaxy would see a very different universe than we do. Most galaxies would have vanished beyond the horizon. The observable universe would appear much emptier, much darker, much more isolated. Any astronomers living in that distant era might conclude they live in a universe containing only their local galaxy group, unaware that trillions of galaxies exist beyond their cosmic horizon. But here's what keeps cosmologists up at night. If we're living inside an observable bubble with a horizon beyond which we cannot see, then space doesn't just stop at that horizon. The universe doesn't end just because we can't see any farther. Logic, mathematics, and observation all suggest that space continues beyond our cosmic horizon. The question is, what's out there? And the answer, increasingly, appears to be something far stranger than most people imagine. The mathematics of cosmic inflation, the theory that describes how the universe expanded in its first fraction of a second, suggests that the observable universe is just a tiny bubble in something much, much larger. Inflation theory, developed in the 1980 seconds by physicists like Alan Guth and André Linde, proposes that in the first 10 to the negative 32 seconds after the Big Bang, space underwent a period of exponential expansion, growing faster than light, doubling in size over and over again in unimaginably brief intervals. This inflationary expansion solved several problems in cosmology, explaining why the universe appears so uniform in all directions and why space appears flat rather than curved. But it also made a startling prediction. The region that inflated and that became our observable universe was just one small patch in a much larger volume of space. The rest of that space should still exist beyond our horizon. If inflation is correct, and the evidence strongly suggests it is, then our observable universe is a sphere 93 billion light-years across, floating in an ocean of space that could be trillions, quadrillions, or even infinite light-years in extent. Everything we've ever seen or ever will see is contained in a tiny bubble, and that bubble is surrounded by something vast and unreachable. When physicists talk about what exists beyond the observable universe, they're not speculating wildly. They're following the mathematics of general relativity and quantum field theory to their logical conclusions. And those conclusions point towards something deeply strange. Space itself, the fundamental fabric of reality, doesn't care about our cosmic horizon. It continues, it persists. It exists whether we can see it or not. The question isn't whether something exists beyond the edge of the observable universe. The question is what that something looks like, how it's structured, and whether it operates according to the same physical laws we observe inside our cosmic bubble. And that's where the evidence, strange as it may seem, begins to pile up. There are anomalies in the oldest light in the universe, irregularities in the cosmic microwave background that shouldn't exist if our observable universe were all there is. There are patterns in the distribution of galaxies that suggest influences from beyond our horizon. There are theoretical frameworks that predict not just more space beyond the edge, but entirely different kinds of space, different physical laws, different dimensions of reality itself. We're standing at the edge of the greatest mystery in physics, staring out at a cosmic horizon that separates the knowable from the unknowable. And the evidence is starting to suggest that what lies beyond might be far more complex, far more diverse, and far stranger than anything we've encountered inside our observable bubble. The universe we see is not the universe that exists, and the part we can't see might hold secrets that would fundamentally rewrite everything we think we know about reality. Scientists, looking at the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space, have found something that shouldn't be there. Anomalies, irregularities, patterns that suggest influences from beyond the cosmic horizon. These aren't subtle quirks that scientists are overinterpreting. These are statistically significant deviations from what the standard model of cosmology predicts. And they're forcing physicists to confront the possibility that our observable universe is being affected by something we cannot see. The cosmic microwave background, often abbreviated as CMB, is the oldest light in the universe. It was released 380,000 years after the Big Bang, when the universe had cooled, enough for atoms to form, allowing light to travel freely through space for the first time. Before this moment, the universe was a hot, dense plasma where photons constantly scattered off charged particles. After recombination, when electrons and protons combined to form neutral hydrogen, photons could stream freely through the cosmos. That ancient light, stretched by cosmic expansion to microwave wavelengths, is what we detect today as the CMB. It fills the entire universe, coming from every direction in the sky, a relic from the infancy of time. In the 1,960 seconds, when Arno Penzias and Robert Wilson accidentally discovered the CMB using a radio antenna at Bell Labs, they found that it was remarkably uniform. No matter which direction they pointed their antenna, they detected the same faint microwave hiss. This uniformity was one of the great confirmations of Big Bang cosmology. If the universe began in a hot, dense state and has been expanding ever since, we'd expect to see exactly this kind of thermal radiation filling all of space. But as technology improved and scientists mapped the CMB in greater detail, they discovered tiny variations in temperature, hot and cold spots that differ by only a few millionths of a degree. These temperature fluctuations aren't random noise. They're the seeds of cosmic structure, slight density variations in the early universe that would eventually grow into galaxies, galaxy clusters, and the vast cosmic web of matter we see today. NASA's Cosmic Background Explorer satellite, launched in 1989, created the first detailed map of these temperature variations. The Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided even finer resolution. And the European Space Agency's Planck satellite, which operated from 2009 to 2013, gave us the most detailed map of the CMB we've ever had. These missions revealed a universe that is extraordinarily uniform on large scales, with temperature variations following a pattern that matches predictions from inflationary cosmology almost perfectly. Almost, but not quite. There are anomalies in the CMB that have troubled cosmologists for decades. The most famous of these is the cold spot, a region roughly 70 degrees across in the direction of the constellation Eridanus, where the cosmic microwave background is significantly colder than the surrounding areas. This isn't a tiny fluctuation. The cold spot is about 70 microkelvins, colder than expected, a difference that's small in absolute terms but enormous compared to the typical variations we see elsewhere in the CMB. When WMAP first detected the cold spot in 2004, some scientists dismissed it as a statistical fluke, an unlikely but not impossible random fluctuation. But when Planck confirmed the cold spot with even better precision, that explanation became harder to accept. The probability of such a large temperature deficit appearing by chance is less than 1%. Not impossible, but unlikely enough to demand explanation. Several theories have been proposed to explain the cold spot. Some suggest it's caused by a supervoid, an enormous region of space containing less matter than average, sitting between us and the CMB. As light from the CMB passes through this void, it experiences a phenomenon called the integrated Sachs-Wolf effect, where photons lose energy climbing out of gravitational wells in an expanding universe. But surveys of the cold spot region haven't found a void large enough or empty enough to account for the full temperature deficit. Another explanation is even more radical. What if the cold spot is evidence of a collision between our universe and another universe beyond our cosmic horizon? In the early moments after the Big Bang, if our bubble universe bumped into or was gravitationally influenced by another bubble, it could have left an imprint on the CMB, a cosmic bruise, marking where the two universes made contact. This idea sounds like science fiction, but it comes from serious theoretical physics. Eternal inflation models predict the formation of multiple bubble universes, each with potentially different physical properties. If these bubbles form close enough to interact during or shortly after their inflationary periods, they could leave observable signatures in the CMB. The cold spot isn't the only anomaly. There's also the axis of evil, a term cosmologists use only half-jokingly to describe an alignment in the largest scale temperature fluctuations of the CMB. When you analyze the CMB for patterns at different angular scales, the biggest patterns, those representing structures hundreds of millions of light-years across, show a preferred orientation. They're not randomly distributed across the sky as they should be. Instead, they align along a particular axis, as if something about the universe's large-scale structure has a directionality to it. This violates one of the fundamental assumptions of modern cosmology, the cosmological principle, which states that the universe should look roughly the same in all directions when viewed on the largest scales. The axis of evil could be a statistical fluke, though the probability of such an alignment occurring by chance is uncomfortably low. Or it could indicate that the observable universe is not quite as uniform as we thought. If our cosmic bubble is part of a larger structure, if we're embedded in something that has directionality or asymmetry on scales larger than our horizon, that could create exactly the kind of alignment we see. Some physicists have proposed that the axis of evil might be evidence that we live in a rotating universe, one with a preferred axis of rotation that affects the distribution of matter and energy on the largest scales. Others suggest it could indicate that the universe has a non-trivial topology, meaning space might be connected to itself in ways that aren't immediately obvious, like a three-dimensional version of a Mobius strip. Then there's the hemispheric asymmetry, another anomaly discovered by Planck. When you divide the sky into two hemispheres, one hemisphere of the CMB shows slightly larger temperature fluctuations than the other. The difference is small, but it's statistically significant and consistent across multiple measurements. This asymmetry violates the assumption that the universe should be isotropic, the same in all directions. If the Big Bang produced a universe that was uniform and expanding equally in all directions, we shouldn't see this kind of lopsidedness in the CMB. Yet there it is, staring back at us from the most detailed maps of the early universe we've ever made. One of the most intriguing explanations for these anomalies involves influences from beyond the cosmic horizon. In eternal inflation scenarios, our observable universe is just one bubble in a vast multiverse. Other bubbles, other universes, could exist nearby in the larger inflating space. If one of these nearby universes exerted gravitational influence on our bubble during the early moments after our Big Bang, it could have left marks in the CMB. Think of it like ripples on a pond. If two drops of water land near each other, the ripples they create can interfere, producing patterns that reveal the presence of both disturbances. Similarly, if our universe and another universe formed close enough to interact gravitationally, the resulting interference could show up as anomalies in the cosmic microwave background. Some physicists have taken this idea further, using computer simulations to model what a collision between bubble universes would look like. The predictions are striking. A collision would create a distinctive pattern in the CMB, a circular region where temperature fluctuations are either enhanced or suppressed, depending on the details of the collision. Several research teams have searched the CMB for these collision signatures. Some claim to have found candidate regions that match the predicted patterns, though the evidence remains controversial. The cold spot, in particular, has been proposed as a potential collision signature, though proving this would require evidence beyond what we can currently extract from CMB data alone. Another line of evidence comes from the large-scale structure of the universe itself. When astronomers map the distribution of galaxies across billions of light-years, they find an intricate cosmic web of filaments, clusters, and voids. This structure grew from the tiny density variations encoded in the CMB, amplified over billions of years by gravity. For the most part, this cosmic web matches what computer simulations predict. But there are hints of anomalies here too. Some studies have found evidence of bulk flows, massive clusters of galaxies all moving in the same direction, with velocities that seem too large to be explained by gravity from structures within the observable universe. The most famous of these is called dark flow, a term coined by Alexander Kashlinsky and his colleagues in 2008. Using data from WMAP, they analyzed the motions of galaxy clusters by looking at how their hot gas distorted the CMB through an effect called the Sunyaev-Zeldovich effect. What they found was unexpected. Hundreds of galaxy clusters across a huge swath of the sky appeared to be moving in the same direction at speeds of 600 to 1,000 kilometers per second, far faster than could be explained by gravitational attraction from any known structures. The implication was startling. These clusters might be responding to gravitational pull from something beyond the cosmic horizon, massive concentrations of matter or energy in regions of space we cannot observe. If true, dark flow would be direct evidence that what exists beyond our observable universe can influence what happens inside it. However, dark flow remains controversial. Later analyses using data from the Planck satellite did not confirm the signal, leading some scientists to conclude that dark flow was an artifact of data processing or statistical noise. But Kashlinsky and his team have continued to defend their findings, pointing to independent analyses that support the existence of bulk flows on large scales. The debate continues, with some cosmologists viewing dark flow as tentative evidence of super-horizon influences, while others remain skeptical until more definitive observations can be made. There's also the mystery of cosmic voids, enormous regions of space that contain far fewer galaxies than average. Some of these voids are so large they seem to violate predictions from the standard model of cosmology. The largest known void, the KBC void, appears to be roughly 2 billion light-years across, with Earth sitting near its center. This creates another puzzle. If we're located in an unusually empty region of space, it could affect how we measure the expansion rate of the universe, potentially explaining why different measurement methods give different values. For the Hubble constant, this discrepancy, known as the Hubble tension, has been one of the biggest problems in cosmology for the past decade. But the existence of such large voids raises deeper questions. How did they form? Why are some voids so much larger than our models predict? Could they be influenced by structures beyond the cosmic horizon, gravitational influences from neighboring bubble universes, or massive concentrations of dark matter extending beyond our observable sphere? Some of the most radical ideas about what exists beyond the observable universe come from string theory and its extensions. These theoretical frameworks suggest that our universe might have extra dimensions beyond the familiar three of space and one of time. If these extra dimensions exist, and if they're large enough to affect gravity on cosmic scales, they could create gravitational influences that reach across the cosmic horizon. Matter and energy in regions beyond our observable universe might exert gravitational pull through these extra dimensions, affecting the distribution of galaxies and the flow of matter in ways that appear anomalous when analyzed using conventional three-dimensional physics. Another piece of evidence, though more speculative, comes from observations of extremely distant quasars and galaxies. Some of the most distant objects Webb has observed appear to be more massive and more structured than they should be given their age. These early galaxies and supermassive black holes pose a timing problem. According to our standard understanding of cosmic evolution, there simply wasn't enough time after the Big Bang for such massive objects to form. This could indicate that our models of early universe physics are incomplete. Or it could suggest that these objects were seeded by influences from beyond the observable universe, perhaps by density perturbations that originated in the larger inflating space, before our local patch underwent its own inflationary expansion. The evidence for something beyond the cosmic horizon is fragmentary, controversial, and often debated, but it's accumulating. The CMB anomalies, potential bulk flows, unusually large voids, and precocious early galaxies all point toward a universe that's more complex than the simple models suggest. These observations don't prove that other universes exist beyond our horizon, but they're consistent with that possibility. They're exactly the kinds of signatures we might expect to see if our observable universe were just one bubble in a larger multiverse, influenced by gravitational interactions with structures beyond our cosmic reach. What makes these anomalies so compelling is that they keep appearing despite efforts to explain them away. Every time a new, more precise measurement is made, the hope is that these irregularities will disappear, revealed as artifacts of limited data or statistical flukes. But instead, they persist. The cold spot is still there. The axis of evil remains aligned. The hemispheric asymmetry continues to divide the sky. These features are real, etched into the oldest light in the universe. The question is no longer whether they exist, but what they mean. For scientists working at the boundary of observational cosmology, these anomalies represent both a frustration and an opportunity. They're frustrating because they don't fit neatly into the standard cosmological model that has been so successful at explaining almost everything else we observe. But they're also an opportunity, a chance to glimpse something beyond the reach of conventional observation, to infer the existence of regions and structures that would otherwise remain forever hidden behind the cosmic horizon. In a very real sense, these anomalies might be our only window into what exists beyond the edge of the observable universe. If we're clever enough to interpret them correctly, they could reveal the shape and nature of the larger reality in which our cosmic bubble floats. The leading theories about what exists beyond the observable universe range from the relatively mundane to the utterly reality-shattering. At one end of the spectrum is the simplest possibility. More space, essentially identical to what we see inside our cosmic bubble, extending perhaps infinitely in all directions, with more galaxies, more stars, more planets, arranged in patterns similar to the cosmic web we observe nearby. At the other end are theories that suggest our universe is one bubble in an infinite multiverse, surrounded by other universes with different physical laws, different numbers of dimensions, different values for fundamental constants. Each bubble a separate reality with its own unique properties. The most conservative extrapolation is that the universe simply continues beyond our horizon. If the observable universe is roughly uniform in all directions, the simplest assumption is that this uniformity extends beyond what we can see. Inflation theory predicts that the patch of space that underwent inflationary expansion was vastly larger than our current observable universe. If that inflating region was initially homogeneous, then regions beyond our cosmic horizon should look roughly similar to what we observe nearby. This means more of the same cosmic web, more galaxy clusters connected by filaments of dark matter, more voids, more of everything that makes up the large-scale structure of the observable universe. But here's where things get interesting. If space continues beyond our horizon, and if space is infinite, which many solutions to Einstein's equations suggest is possible, then the implications become profound and strange. An infinite universe containing a finite number of possible particle configurations means that eventually, given enough distance, patterns must repeat. There are only so many ways to arrange atoms in a given volume of space. If space is truly infinite, then every possible arrangement must occur not just once, but infinitely many times. This leads to the disturbing conclusion that in an infinite universe, there are an infinite number of regions identical to our observable universe. Not similar, identical. Same galaxies, same stars, same planets, same version of you reading these words. The mathematics is inescapable. In an infinite space with finite variations, repetition is not just possible, but inevitable. The distance to the nearest identical region would be staggeringly large, far beyond our cosmic horizon. Estimates based on quantum mechanics and the number of possible particle states suggest that an exact duplicate of our observable universe would appear roughly 10 to the power of 10 to the power of 115 meters away. That's a 1 followed by 10 to the 115 zeros meters. To put that in perspective, the observable universe is only about 10 to the 27 meters across. The nearest identical copy of our cosmic bubble would be so incomprehensibly distant that no physical interaction between our region and that duplicate will ever be possible. But mathematically, if space is infinite, such duplicates exist, and not just one duplicate, infinitely many. This leads to even stranger implications. Between here and the nearest exact duplicate, there would be regions that are almost identical to ours, differing in only minor ways. A universe where you made a different choice this morning. A universe where the asteroid that killed the dinosaurs missed Earth. A universe where human civilization took a different path. If the universe is infinite, all possible variations exist somewhere, separated by vast distances but equally real. This isn't speculation or philosophy. It's a direct mathematical consequence of an infinite universe with finite complexity, but the infinite continuation of similar space is just the beginning. More exotic theories suggest that what exists beyond our cosmic horizon might be fundamentally different from anything inside our observable universe. This brings us to the concept of bubble universes, sometimes called pocket universes, arising from the process of eternal inflation. Inflation theory explains the early universe's expansion, but the mathematics of inflation contains a surprising feature. Once inflation starts in some region of space, it never completely stops everywhere at once. Instead, inflation ends in some patches, while continuing in others. The patches where inflation ends become universes like ours, while the regions where inflation continues keep expanding exponentially, creating new space that eventually spawns more patches where inflation ends. This process is eternal. It never stops. New bubble universes are constantly forming within the eternally inflating space, each bubble representing a separate universe with its own Big Bang, its own evolution, its own galaxies and stars. These bubbles expand and evolve, but they're embedded in a larger, inflating background that grows faster than the bubbles themselves. This means the bubbles never merge or interact significantly after they form. Each universe is causally disconnected from the others, separated by vast regions of still inflating space. Our observable universe would be just one such bubble, and beyond our cosmic horizon, at distances we can never reach, other bubbles exist, each containing its own observable universe potentially vastly different from ours. The truly radical aspect of eternal inflation is that it predicts variation in physical laws across different bubbles. According to string theory and its landscape of possible vacuum states, different bubbles might settle into different configurations of quantum fields during their formation. These different configurations would result in different values for fundamental constants like the strength of electromagnetism, the mass of particles, even the number of spatial dimensions that expand to macroscopic scales. Some bubbles might have stronger gravity, making star formation happen differently. Some might have different particle physics, creating chemistry unlike anything we know. Some might have no stars at all, just diffuse clouds of matter that never condense. Some might be far more hospitable to complex structures than our universe. This landscape of bubble universes is sometimes called the multiverse, though that term can mean different things in different contexts. In the context of eternal inflation, the multiverse is the collection of all bubble universes formed from the eternal inflating background. Each bubble has its own observable universe, its own cosmic horizon, its own physical properties, and because inflation is eternal, the number of bubbles is infinite. There's no edge to this multiverse, no final bubble beyond which nothing exists. New bubbles are always forming. Inflating space always generates new regions where inflation ends and universes begin. We exist in one bubble among infinitely many, separated from our nearest neighboring universe, by distances that make the size of our observable universe seem infinitesimally small. The implications for what exists beyond our cosmic horizon depend on how far away the nearest other bubble is. If we're lucky, or unlucky depending on your perspective, the nearest neighboring bubble universe might have formed close enough to ours that we can detect its gravitational influence or even evidence of a collision. Some of the CMB anomalies we discussed earlier might be signs of such interactions. But it's equally possible that the nearest bubble is so far away that no signal from it could ever reach us. No gravitational influence could ever affect our evolution. We might be profoundly alone in our bubble, surrounded by eternally inflating space that stretches beyond comprehension before reaching the next universe. Some theories go even further, suggesting that what exists beyond our observable universe isn't just more space or other bubble universes, but higher dimensional structures that our three-dimensional minds struggle to conceptualize. In string theory, the fundamental building blocks of reality aren't particles, but tiny vibrating strings of energy. For the mathematics of string theory to work, it requires extra spatial dimensions beyond the three we experience. Early formulations required 10 total dimensions, 9 of space and 1 of time. More recent versions, M theory, suggest 11 dimensions. The reason we don't perceive these extra dimensions is that they're compactified, curled up so small that their effects only become noticeable at the Planck scale, roughly 10 to the negative 35 meters. At everyday scales, and even at the scales accessible to our most powerful particle accelerators, these extra dimensions are invisible. But what if beyond our cosmic horizon, the structure of dimensions is different? What if there are regions where some of these extra dimensions are not compactified, where they expand to macroscopic or even cosmic scales? Such regions would be utterly alien to our experience. A universe with 4 or 5 large spatial dimensions would have gravity that falls off differently with distance, changing the dynamics of star formation, galaxy formation, even the stability of atoms. Orbital mechanics wouldn't work the same way. Planets probably couldn't form stable orbits around stars. Life as we know it would be impossible. But that doesn't mean such regions couldn't exist. The mathematics allows for it. String theory doesn't require that all parts of the larger space have the same number of expanded dimensions. Some cosmologists have proposed that our three-dimensional observable universe might be a brane, a three-dimensional membrane floating in a higher dimensional space called the bulk. Other branes might exist in this bulk, parallel to ours, but separated by tiny distances in the extra dimensions. If these brane universes exist, they would be literally right next to us in the extra-dimensional direction, yet completely invisible and inaccessible because we're confined to our three-dimensional brane. The only force that might be able to cross between branes is gravity, which in some formulations of string theory propagates through the bulk rather than being confined to branes. This could explain why gravity is so much weaker than the other fundamental forces. Maybe gravity's strength is diluted because it's spreading out through extra dimensions while electromagnetism and the nuclear forces are confined to our brane. If brane worlds exist, what lies beyond our cosmic horizon might not be more three-dimensional space, but a higher dimensional bulk containing multiple branes, each one a separate universe with potentially different physical properties. These branes might occasionally collide, and some theorists have proposed that the Big Bang itself was the result of a collision between our brane and another. The cosmic microwave background anomalies might be echoes of that collision, imprints left on our universe by the impact. This idea, called the ekpyrotic universe model, offers an alternative to traditional Big Bang cosmology, suggesting that the universe goes through cycles of collision and expansion, with each collision resetting the universe and beginning a new cycle. Then there are theories that venture into even more speculative territory. What if what exists beyond the cosmic horizon is not space at all, but something more fundamental? Some physicists have proposed that space itself is emergent, a phenomenon that arises from more basic underlying structures. In theories of quantum gravity, particularly in approaches like loop quantum gravity and causal set theory, space is not continuous but discrete, made up of tiny indivisible units at the Planck scale. The smooth space we experience is like the surface of a pool of water, smooth and continuous at large scales, but made of discrete molecules at small scales. If space is emergent, then beyond the cosmic horizon, where our theories break down and our observations cannot reach, the nature of space itself might be different. Perhaps the underlying quantum geometry that gives rise to space in our observable universe transitions into different configurations beyond our horizon, creating regions with different spatial properties, different dimensionality, different connectivity. Some of the most mind-bending proposals come from applying quantum mechanics to the entire universe. In the many worlds interpretation of quantum mechanics, every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. Applied cosmologically, this would mean that beyond our cosmic horizon, there might not be a single definite state of space and matter, but a quantum superposition of all possible states. Every possible arrangement of particles, every possible outcome of every quantum event since the Big Bang exists simultaneously in different trace branches of the universal wave function. What we see as our observable universe is just one branch, one specific outcome of the quantum evolution. Beyond our horizon, the quantum nature of reality might be more apparent, with space existing in states that are fundamentally indeterminate until observed. Another radical idea comes from the holographic principle, derived from studying black holes and quantum gravity. The holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a three-dimensional image encoded on a two-dimensional hologram. Applied to cosmology, This leads to the proposal that our three-dimensional universe might actually be a holographic projection from information encoded on a two-dimensional surface at the cosmic horizon. If this is true, then what exists beyond the observable universe might be the actual fundamental reality, a two-dimensional informational structure from which our process, three-dimensional experience emerges. The galaxies, stars, and space we observe would be holographic projections, real in their own right, but ultimately encoded in a lower dimensional boundary. Each of these theories makes different predictions about what exists beyond the cosmic horizon, but they share a common theme. The universe is likely far stranger and more complex than the portion we can observe. Whether it's infinite space filled with duplicate regions, bubble universes with different physical laws, higher dimensional brains, emergent spatial geometries, quantum superpositions, or holographic projections. The leading edge of theoretical physics points toward a reality that extends far beyond our observable bubble and operates according to principles that challenge our most basic intuitions about space, time, and existence. What would it actually look like if you could somehow transcend the cosmic horizon and see what exists beyond? This question might seem meaningless. After all, if we can't observe beyond the horizon, how can we describe what it looks like? But theoretical physics combined with mathematical modeling allows us to construct detailed mental images of these otherwise invisible realms, and those images are both beautiful and terrifying in their implications. Imagine you have a magic telescope, one that isn't limited by the speed of light or the age of the universe, one that can show you what exists beyond the cosmic horizon right now. Point this impossible device toward the edge of the observable universe and keep looking outward. What would you see? If the simplest theories are correct, you'd see more of the same. The cosmic web would continue, filaments of dark matter and galaxies stretching on and on, clusters connected by bridges of matter, voids between them, growing larger and more numerous as you look to greater distances. The galaxies themselves might look slightly different, their specific shapes and sizes varying randomly, but their overall character would be familiar. Spirals, ellipticals, irregulars, all following the same physical processes that govern galaxy formation in our observable region. Keep going farther, to distances 1,000 times beyond our cosmic horizon, 1,000,000 times, 1,000,000,000. If space is homogeneous and infinite, the cosmic web just continues. More galaxies, more clusters, more large-scale structure repeating endlessly. But here's where the mind-bending implications of infinity begin to surface. If you could travel far enough, you'd eventually reach a region that looks exactly like our local cosmic neighborhood. Not similar, exactly the same. The same arrangement of galaxy clusters, the same Virgo supercluster, the same local group, the same Milky Way, the same solar system, the same Earth. An exact duplicate, so far away that the distance is effectively infinite in any practical sense, but mathematically certain to exist if space is truly infinite. The first duplicate would be just the beginning, keep going, and you'd find another, then infinitely many copies of our entire observable universe, each separated by incomprehensible distances, but identical down to the quantum state of every particle. Between these exact duplicates would be near duplicates, regions that match our observable universe except for minor variations. A version where one photon took a slightly different path during the formation of the CMB. A version where one galaxy formed 100 years earlier. The variations would range from trivial to profound, but all possible variations would exist somewhere in the infinite expanse. This infinite duplication wouldn't just apply to large-scale structures. It would extend down to the smallest scales. If you're reading these words, there are infinite copies of you doing exactly the same thing right now in other regions of an infinite universe. There are also infinite variations of you making different choices, living different lives, existing in slightly different versions of Earth's history. Every possible configuration of particles that could form a version of you exists somewhere in an infinite space. This isn't mysticism or speculation. It's pure mathematics. Infinity combined with finite complexity necessitates repetition. But let's consider more exotic possibilities. What if beyond our cosmic horizon, you don't see more of the same? What if you could perceive the transition zones where our bubble universe borders the eternally inflating space that surrounds it? Inflation is expansion on steroids, space doubling, and doubling again on timescales far shorter than any normal cosmic process. If you could watch this happen, you'd see space itself stretching so rapidly that quantum fluctuations in the energy fields become frozen into the fabric of reality. The smooth, inflating space would be like a sea of potential, a quantum foam where virtual particles and energy fluctuations dance at the edge of existence. This isn't empty space in any conventional sense. It's space pregnant with possibility, its energy density dominated by the inflaton field, the mysterious scalar field that drives inflation. At some point in this eternally inflating sea, you'd see bubbles forming. Not bubbles in the ordinary sense, but regions where inflation suddenly ends, where the inflaton field decays and its energy converts into matter and radiation, creating a localized Big Bang. Each bubble would appear as a sphere of expanding space, its interior filled with hot matter and energy, rapidly cooling and expanding, eventually forming galaxies and stars. Our observable universe is the interior of one such bubble. Beyond our cosmic horizon, you might see the walls of our bubble, the boundary between our post-inflationary space and the still inflating background. This boundary would be expanding outward at nearly the speed of light, a shell of space-time separating two fundamentally different regimes. Beyond our bubble's wall, you'd see the inflating space continuing, and scattered through it at vast distances, other bubbles. Each bubble would be its own universe, causally disconnected from ours, expanding and evolving independently. Some bubbles might be older than ours, their interiors filled with ancient galaxies in the late stages of stellar evolution. Some might be younger, still in their first billion years of existence, just beginning to form stars. Some might be so young that they're still filled with hot primordial plasma, opaque and featureless. And because the inflating background grows faster than the bubbles themselves, these bubble universes would never touch. The space between them would expand faster than they could grow, maintaining eternal separation. Now imagine you could perceive across multiple bubbles, seeing how each one's physical laws differ. In one bubble, the electromagnetic force might be 10% stronger, making chemistry work differently. Stars in that universe would burn, hotter and faster, living shorter lives. Planets would hold their atmospheres more tightly. Complex molecules might be more stable or less stable, depending on how the altered force affects atomic structure. Look at another bubble, and perhaps the weak nuclear force is different, changing the rates of radioactive decay and the processes inside stars. That universe might have more or less heavy elements, affecting what kinds of planets can form. Another bubble might have different values for the cosmological constant, the energy density of empty space. If it's too large, space expands so rapidly that galaxies never form. If it's negative, the universe might collapse back on itself before stars have time to ignite. The variation could be even more dramatic. Some bubbles might have different dimensionality. Instead of 3 spatial dimensions, imagine a bubble with 4. Visualization is difficult because our brains are wired for 3-dimensional space, but mathematically, 4-dimensional space allows for much more complex geometry. Spheres can be linked and unlinked in ways impossible in 3 dimensions. Orbits behave differently. Gravity falls off as 1 over distance cubed instead of distance squared, making stable planetary systems probably impossible, but allowing for entirely different kinds of structures to form. A 4-dimensional bubble universe would be alien beyond comprehension, operating according to geometric principles that have no analog in our experience. Some bubbles might have no large spatial dimensions at all, their extra dimensions remaining compactified, creating a universe that exists only as a lower dimensional structure embedded in the higher dimensional bulk. Or imagine a bubble where time itself operates differently. General relativity allows for spacetimes with multiple time dimensions or where time and space are less clearly distinguished. In such a universe, causality might work in ways we can't even conceptualize. The flow from past to future might be replaced by something more complex, a network of causal relationships that don't form a simple linear sequence. What about the higher dimensional bulk in brain world scenarios? If you could perceive the extra dimensions, you'd see our three-dimensional universe as a brain, a membrane-like structure floating in a higher dimensional space. This brain would appear thin in the extra dimensions but vast in our familiar three dimensions. Other brains might be visible, separated from ours by minuscule distances in the extra dimensions, perhaps just micrometers or even smaller. These parallel brains would be entire universes themselves, three-dimensional spaces potentially filled with galaxies and stars, yet completely invisible to us, because light can't propagate through the extra dimensions. The only interaction between brains would be gravitational, gravity's influence leaking through the bulk. The bulk itself might not be empty. Some theories suggest it could be filled with exotic matter or energy, perhaps even its own structures formed from higher dimensional physics. Imagine objects that exist fully in the higher dimensional bulk, structures that would appear to us as three-dimensional cross-sections, like how a three-dimensional sphere passing through a two-dimensional plane would appear to the plane's inhabitants as a circle that grows and shrinks. Bulk objects passing near our brain could create gravitational anomalies, influences that seem to come from nowhere because their sources exist in dimensions we can't perceive. If the holographic principle describes the true nature of reality, the view beyond the cosmic horizon would be even more abstract and strange. The three-dimensional universe we experience might be an emergent phenomenon projected from information encoded on a two-dimensional boundary at the cosmic horizon. From outside the hologram, if such a perspective were possible, you might see this boundary as a vast, two-dimensional surface embedded in a higher dimensional space. All the information about every galaxy, every star, every particle in our observable universe would be encoded on this surface as quantum information, perhaps as patterns of entangled quantum states. The three-dimensional universe we inhabit would emerge from correlations in this boundary information, like how a holographic image appears three-dimensional, even though it's encoded on a two-dimensional film. What exists beyond this holographic boundary is one of the deepest questions in theoretical physics. Some formulations suggest that what we call the interior of the universe and its boundary are actually dual descriptions of the same physics, two different ways of describing one reality. In this view, asking what exists beyond the boundary might be like asking what's north of the North Pole. It's not that there's nothing there. The question itself might not have a meaningful answer because the boundary is the fundamental reality. The simulation hypothesis offers another possibility for what exists beyond the cosmic horizon. If our universe is a simulation running on some unimaginably advanced computational substrate, then beyond the observable universe might be the limits of what the simulation has bothered to compute. Like in a video game where only the visible region is rendered in detail, while distant areas exist in low resolution or not at all, our observable universe might be the actively computed region, while beyond the horizon is unrendered, existing only as potential until observation or measurement requires it to be computed. The edge of the observable universe would then be a computational boundary, the limit of the simulation's active rendering. Beyond it might be compressed data, simplified algorithms, or nothing at all until the simulation decides to expand the rendered region. Each of these visions of what lies beyond the cosmic horizon is rooted in serious theoretical physics, yet each paints a picture so different from everyday experience that they barely seem to describe the same reality. Some show infinite repetition of familiar structures. Others reveal bubble universes with alien physics. Some require extra dimensions we can't perceive. Others suggest our reality is holographic or simulated. The truth might involve aspects of several of these pictures or something entirely different that we haven't yet imagined. What they all share is a fundamental departure from the naive assumption that the universe we see is all there is. They force us to confront the possibility that our cosmic bubble is just one small part of something vastly larger and stranger than we ever conceived. The question of why we can never see beyond the cosmic horizon brings us back to fundamental physics, to the nature of light, space, and time. The barrier isn't technological. It's not that we need better telescopes or more sensitive detectors. The barrier is woven into the fabric of reality itself, arising from the speed of light, the age of the universe, and the accelerating expansion of space. These aren't limitations we can overcome with clever engineering. They're absolute boundaries imposed by the laws of physics as we understand them. Light travels at a fixed speed in vacuum, approximately 299,792 kilometers per second. This is the speed limit of the universe, the fastest that information can propagate through space. Nothing with mass can reach this speed, and nothing, not even light, can exceed it. This speed limit means that light from distant objects takes time to reach us. The farther away something is, the longer its light has been traveling. When we look at distant galaxies, we're seeing them not as they are now, but as they were when the light left them millions or billions of years ago. The observable universe is defined by how far light can have traveled since the Big Bang. Light that originated farther away than our cosmic horizon simply hasn't had enough time to reach us yet. You might think that we just need to wait. Given enough time, light from increasingly distant regions should eventually reach us, expanding our observable universe. And to some extent, this is true. Every year, light from regions about 1 light-year beyond our current cosmic horizon enters our observable bubble. The cosmic horizon is constantly expanding, revealing new regions of space. But here's the problem. The expansion of space is accelerating. Driven by dark energy, the universe isn't just growing, it's growing faster and faster. Distant galaxies aren't just moving away from us, they're moving away at speeds that increase with distance. At a certain distance, currently about 16 billion light-years away, the expansion of space is carrying galaxies away from us faster than light can travel toward us. This creates the cosmological event horizon. Anything beyond this boundary is not just currently invisible, it will remain forever. Invisible because light from those regions is fighting a losing battle against the expansion of space. Imagine a photon emitted from a galaxy just beyond the cosmological event horizon, traveling toward us at the speed of light. It's moving in our direction, but the space between us and that galaxy is expanding faster than the photon can cross it. The photon makes progress toward us, but the distance it needs to travel is increasing faster than it's moving. It's like running on a treadmill that's accelerating faster than you can run. You're moving forward, but you're losing ground. As cosmic expansion continues to accelerate, the cosmological event horizon actually shrinks in terms of the physical distance to the galaxies it contains. Galaxies that we can see today will eventually cross this horizon and disappear from view. Their light will become so redshifted by expansion that it will fade to undetectable wavelengths. In the far future, trillions of years from now, observers in our galaxy will see a much emptier universe. Most galaxies will have slipped beyond the cosmological event horizon, their light stretched into oblivion. The observable universe will appear to contain only our local galaxy group, gravitationally bound together, and thus immune to cosmic expansion, surrounded by an expanding void that grows darker and emptier with each passing eon. This future isolation is built into the nature of accelerating expansion. Dark energy, whatever it is, appears to have a constant density throughout space. As space expands, more dark energy comes into existence, maintaining this constant density. The more space expands, the more dark energy exists, driving faster expansion, creating more space, and so on in an accelerating feedback loop. Unless the nature of dark energy changes, and there's no indication it will, this acceleration will continue forever. The universe will expand faster and faster, pushing more and more matter beyond the cosmological event horizon, until only gravitationally bound structures remain visible. There's another fundamental barrier to seeing beyond the cosmic horizon, one that exists even without acceleration. The cosmic microwave background represents the farthest back in time we can see using light. Before the CMB was emitted, roughly 380,000 years after the Big Bang, the universe was opaque. It was a hot, dense plasma where photons constantly scattered off charged particles. Light couldn't travel freely through this plasma any more than light can travel freely through fog. When we look at the CMB, we're seeing the moment when the universe became transparent, when it cooled enough for electrons and protons to combine into neutral atoms, allowing photons to stream freely through space for the first time. Everything before that moment is hidden behind a wall of plasma. We can't use light to see earlier than the CMB, but that doesn't mean we're completely blind to earlier times. Gravitational waves and neutrinos could carry information from the first moments after the Big Bang because they interact much more weakly with matter than photons do. Gravitational waves would have propagated freely through the opaque plasma that trapped light, carrying information about violent processes in the early universe. Neutrinos, ghostly particles that barely interact with matter, could escape from even earlier times. The cosmic neutrino background, if we could ever detect it, would show us the universe as it was just 1 second after the Big Bang, long before the CMB formed. But even these exotic messengers have limits. They can't show us what existed before the Big Bang or beyond the cosmic horizon. Some physicists have proposed ways to indirectly probe beyond the cosmic horizon, methods that don't rely on receiving light or other signals from those distant regions. One approach involves looking for gravitational effects. If massive structures exist beyond our horizon, they might exert gravitational pull that affects matter within our observable universe. The dark flow phenomenon, controversial though it remains, represents this kind of indirect detection. If galaxy clusters are indeed being pulled by something beyond our horizon, careful measurements of their motions could reveal properties of that external influence, even though we can never see the source directly. Another potential method involves studying the quantum vacuum. In quantum field theory, even empty space is filled with virtual particles constantly popping in and out of existence. These quantum fluctuations are affected by the large-scale structure of space. If the universe has exotic topology, meaning space is connected to itself in unusual ways, it could create specific patterns in the quantum vacuum that we might be able to detect. For example, if the universe wraps back on itself like the surface of a sphere or a torus, certain wavelengths of quantum fluctuations would be forbidden or enhanced depending on the exact topology. Precise measurements of the Casimir effect or other quantum vacuum phenomena might reveal topological features of the universe on scales larger than our cosmic horizon. Similarly, if our universe is one bubble in an eternal inflation scenario, the collision between our bubble and a nearby bubble during or shortly after formation could have left permanent scars in the structure of space. These collision signatures would show up as specific patterns in the cosmic microwave background or in the distribution of matter. Several research groups have searched for such signatures with tentative claims of detection, but no definitive proof yet. If confirmed, these collision scars would represent indirect evidence of what exists beyond our horizon, proof that other bubble universes exist, even though we can never observe their interiors. The holographic principle offers another potential route to understanding what lies beyond the horizon. If the universe is fundamentally holographic, with all information about the interior encoded on a boundary, then studying the quantum properties of space near the cosmic horizon might reveal information about the larger structure in which our universe is embedded. This is highly speculative, but some theorists have proposed that careful analysis of quantum entanglement patterns across large distances could reveal whether our universe has holographic structure and potentially even constrain properties of the boundary or the bulk space beyond it. Despite these clever approaches, the fundamental barriers remain. We cannot receive light or any signal traveling at or below light speed from beyond the cosmological event horizon because the expansion of space prevents those signals from ever reaching us. We cannot see earlier than the cosmic microwave background using photons because the universe was opaque before that time. We cannot observe other bubble universes in eternal inflation scenarios because they're causally disconnected from ours, separated by regions of space expanding faster than light. These are not technological limitations. They're built into the structure of space-time itself. Some physicists have speculated about using exotic phenomena to bypass these limits. If wormholes exist, traversable shortcuts through space-time, they might connect regions of space that are beyond each other's cosmic horizons. Traveling through such a wormhole could theoretically allow you to reach parts of the universe that are receding faster than light, bypassing the normal light travel restrictions. But wormholes remain purely theoretical. Even if they exist, maintaining a traversable wormhole would require exotic matter with negative energy density, something that might violate fundamental laws of physics. And creating a wormhole, connecting our observable universe to a region beyond our horizon, would require being able to access that distant region in the first place, which brings us back to the original problem. Faster than light travel, if it were possible, could also potentially allow us to reach beyond the cosmic horizon. Various theoretical proposals exist, from Alcubierre warp drives to quantum tunneling on macroscopic scales. But all of these ideas require physics that goes beyond our current understanding and likely violates known physical laws or requires resources on scales we can barely imagine. The Alcubierre drive, for instance, would require negative energy densities larger than the mass energy of observable galaxies. Even if we could build such a device, using it to travel faster than the expansion of space itself would be an engineering challenge of unimaginable proportions. The reality is that the cosmic horizon represents a permanent, fundamental limit on what we can directly observe. Regions beyond this boundary are not just currently inaccessible, they're absolutely inaccessible, cut off from us by the expansion of space in a way that no technology can overcome. The light from those regions will never reach us. Signals cannot propagate between causally disconnected parts of the universe. The cosmic horizon is as absolute a barrier as exists in physics, as impenetrable as the event horizon of a black hole. And just as with a black hole's event horizon, the barrier is not a physical wall, but a boundary in space-time beyond which events cannot influence our region. This permanence of the cosmic horizon has profound implications. It means there are questions we will never be able to answer through direct observation. What exists 100 billion light-years from here? What happened to the matter in regions beyond our horizon? Are there other bubble universes with different physical laws? These questions might have answers, might describe real aspects of physical reality, but we will never be able to confirm those answers through observation. We can theorize, we can build mathematical models, we can look for indirect evidence, but we cannot see beyond the horizon. This is a hard limit on human knowledge, a boundary beyond which empirical science cannot reach, leaving us with theory, mathematics, and speculation as our only tools for understanding what might exist in the cosmic beyond. Yet despite these limitations, the search continues. Scientists are developing new experiments and observations that might offer indirect glimpses of what lies beyond, new ways to test theories about the larger structure of reality, even when direct observation is impossible. These future experiments represent our best hope for understanding the cosmic unknown. One of the most promising avenues involves the next generation of cosmic microwave background experiments. The CMB is a treasure trove of information about the early universe, and each new generation of detectors reveals finer details and subtler features. The Simons Observatory, currently under construction in Chile, will map the CMB with unprecedented precision, measuring its polarization patterns with sensitivity far beyond previous experiments. The CMB-S4 experiment, a proposed network of telescopes at the South Pole and in the Atacama Desert, would push this even further, potentially detecting the faint imprint of gravitational waves from the inflationary period. These primordial gravitational waves, if detected, would be smoking gun evidence for inflation. They would also carry information about the energy scale of inflation and the nature of the inflaton field, helping us understand whether eternal inflation is correct and what the larger structure beyond our cosmic bubble might look like. Different models of inflation make different predictions about the strength and pattern of these primordial gravitational waves. By measuring them precisely, we could distinguish between scenarios where our universe is all there is and scenarios where we're one bubble among many in an eternally inflating multiverse. CMB experiments can also search more carefully for collision signatures. If our bubble universe collided with another bubble during or shortly after inflation, it would leave a distinctive pattern in the CMB, a circular region where temperature and polarization fluctuations differ from the surrounding sky. Several groups have claimed tentative detections of such patterns, but none have been confirmed at high significance. Future CMB experiments with better sensitivity and more complete sky coverage might definitively detect or rule out collision signatures, answering whether we've ever interacted with another universe beyond our cosmic horizon. Gravitational wave astronomy offers another window into the cosmic beyond. The LIGO and Virgo detectors have opened a new era in astronomy by detecting gravitational waves from colliding black holes and neutron stars. These ground-based detectors are sensitive to high-frequency gravitational waves from stellar mass objects. Future space-based detectors like LISA, the Laser Interferometer, space antenna, will detect lower-frequency gravitational waves from supermassive black holes and other exotic sources. But there's also the possibility of detecting ultra-low-frequency gravitational waves that oscillate over cosmic timescales. These ultra-low-frequency gravitational waves could carry information about processes in the very early universe, or even about the larger structure beyond our cosmic horizon. If bubble universes collide or if massive cosmic strings snake through the inflating space beyond our bubble, they might generate gravitational waves that could affect the pattern of matter in our observable universe. Pulsar timing arrays, which use precise measurements of radio pulses from neutron stars to detect gravitational waves with wavelengths of light years, might be sensitive to such signals. The International Pulsar Timing Array and the North American Nanohertz Observatory for Gravitational Waves are already collecting data that might reveal these cosmic-scale gravitational waves. Another approach involves using the universe as a quantum laboratory. Quantum mechanics predicts that the vacuum of space is not truly empty, but filled with quantum fluctuations, virtual particles that briefly appear and disappear. These fluctuations are affected by the large-scale structure of space. If the universe has exotic topology, or if we're embedded in a higher dimensional bulk, it could create specific patterns in the quantum vacuum that we might detect through ultra-precise measurements. The Casimir effect, where two uncharged metal plates attract each other due to quantum vacuum fluctuations, is extremely sensitive to the structure of space. Future experiments measuring the Casimir effect with increasing precision might detect anomalies that point toward exotic topology or extra dimensions. Similarly, experiments with atom interferometers and ultra-cold atoms could potentially detect subtle effects of extra dimensions or non-trivial topology if such features exist. Some proposed experiments aim to test whether our universe might be a simulation. This is inherently difficult because a sophisticated simulation could presumably hide evidence of its own nature. But some theorists have suggested that computational limits might leave detectable signatures. For example, if space is fundamentally discrete rather than continuous, there might be a smallest possible length scale, and physics at that scale might exhibit features suggesting computational structure. Experiments searching for Lorentz invariance violation at very high energies or tests of quantum mechanics at the smallest accessible scales might reveal such signatures, though this remains highly speculative. The James Webb Space Telescope and future observatories will continue to push our view of the early universe to greater distances and earlier times. While they cannot see beyond the cosmic horizon, they can map the universe closer and closer to that boundary, potentially finding anomalies or patterns that suggest influences from beyond. Extremely distant galaxies, their formation and distribution, might carry signatures of the larger structure in which our bubble universe is embedded. If inflation created specific patterns in the density fluctuations that seeded galaxy formation, and if those patterns were influenced by physics beyond our horizon, careful analysis of early galaxy statistics might reveal those influences. Multi-messenger astronomy, combining data from electromagnetic observations, gravitational waves, neutrinos, and cosmic rays, offers a more complete picture of the universe than any single method alone. Some phenomena might leave traces across multiple channels, and correlating these different types of signals could reveal aspects of reality that remain hidden when looking at any single channel. For instance, if exotic structures beyond our horizon create gravitational lensing effects that are too subtle to detect in optical light alone, they might become apparent when combining optical, gravitational wave, and neutrino observations of the same region of sky. Theoretical advances are equally important. Improved understanding of quantum gravity, the long-sought theory that unifies general relativity and quantum mechanics, might reveal new principles that constrain what can exist beyond the cosmic horizon. Different approaches to quantum gravity, string theory, loop quantum gravity, causal dynamical triangulations, make different predictions about the large-scale structure of space and time. As these theories develop and make more specific predictions, we might be able to test them through observations of our own universe, indirectly learning about the larger reality in which we're embedded. Computer simulations of the universe are becoming increasingly sophisticated. By running simulations with different assumptions about what exists beyond the cosmic horizon, cosmologists can predict what signatures those different scenarios would leave in the observable universe. If simulations with a certain type of multiverse structure match our observations better than simulations assuming our observable universe is all there is, that becomes evidence, albeit indirect, for that multiverse scenario. This is similar to how particle physicists use computer simulations to predict what new particles would look like if they existed, then search for those signatures in accelerator data. Perhaps most intriguingly, advances in quantum information theory and quantum computing might offer entirely new approaches to probing the cosmic beyond. The holographic principle and its elaborations suggest deep connections between quantum information, gravity, and the structure of space-time. If these connections can be fully understood and exploited, they might allow us to infer properties of the cosmic horizon and what lies beyond through careful analysis of quantum correlations and entanglement patterns in the space we can observe. This is cutting-edge theoretical work that blends quantum mechanics, general relativity, and information theory in novel ways, and it might open conceptual windows into regions that are otherwise forever beyond our reach. All of these approaches share a common thread. Since we cannot directly observe what exists beyond the cosmic horizon, we must look for indirect evidence, subtle signatures, and anomalies in what we can observe that point toward larger structures beyond our view. It's detective work on a cosmic scale, using every tool available to piece together a picture of reality from fragmentary clues. The cosmic horizon might be an absolute boundary on direct observation, but it's not necessarily a boundary on knowledge. If we're clever enough, patient enough, and lucky enough, we might yet learn profound truths about what lies beyond, even though we can never see it directly. Now we come to the final, most unsettling implication of what might exist beyond the cosmic horizon. If the universe is infinite, as many solutions to Einstein's equations suggest, and if it's filled with matter and energy, following the same physical laws throughout, then something extraordinary and deeply strange must be true. Everything that can exist already exists somewhere beyond our cosmic horizon. Not everything that does exist, but everything that can exist. Every possible arrangement of particles, every possible outcome of every quantum event, every possible variation on the history of matter and energy, all of it exists somewhere in the infinite expanse. This conclusion follows from simple mathematics. There are a finite number of ways to arrange particles in any given volume of space. Quantum mechanics limits the number of possible states a region can have. Once you've exhausted all possible arrangements within a volume the size of our observable universe, any additional similar volumes must contain repeated patterns. In an infinite universe, you don't just get a few repetitions. You get infinite repetitions of every possible configuration. This means that somewhere, incomprehensibly far beyond our cosmic horizon, there's another region of space identical to our observable universe. Same galaxies in the same places, same stars, same planets, same version of Earth, same version of you having the exact same thoughts at the exact same moment. The distance to this duplicate is staggering beyond comprehension. Based on estimates of the number of possible quantum states in a region the size of our observable universe, the nearest exact duplicate would be roughly 10 to the power of 10 to the power of 115 meters away. To write this number out fully, you'd need more zeros than there are atoms in the observable universe. The nearest identical copy of you is so far away that the distance makes the size of the observable universe seem smaller than an atom in comparison. But in an infinite universe, distance is ultimately irrelevant to existence. That duplicate exists, as real and physical as you are, living an identical life in an identical world. And it doesn't stop there. Between here and that first exact duplicate are countless near duplicates, regions that are almost identical to our observable universe, but differ in small ways. A version where one photon in the cosmic microwave background took a slightly different path. A version where one atom in one star underwent a radioactive decay event a moment earlier or later. As you move through the space of possibilities, the differences grow. A version where the asteroid that killed the dinosaurs arrived a day earlier. A version where it missed Earth entirely. A version where you made a different decision this morning. Every possible variation exists somewhere in the infinite expanse, each one as real and physical as the universe you inhabit. This isn't metaphysics or philosophy. It's a direct consequence of infinity combined with finite complexity. If space is infinite and governed by the same physics everywhere, and if there are only finitely many possible quantum states for any given volume, then repetition is mathematically inevitable. The universe doesn't just allow for these duplicates, it demands them. Infinity ensures that every possible arrangement that can exist, and does so infinitely many times. Think about what this means for a moment. Somewhere beyond the cosmic horizon, there's a version of Earth where the Roman Empire never fell, where human civilization took a different path, where the entire course of history unfolded differently, not because of magic or parallel dimensions, but because in an infinite universe, every possible outcome that quantum mechanics allows must occur somewhere. There's a version where life never evolved on Earth. There's a version where an entirely different form of life emerged, creating a biosphere and eventually a civilization completely unlike anything on our Earth. There's a version where intelligence evolved in the oceans rather than on land, where dolphins or octopuses became the dominant technological species. Extend this to the entire universe. Somewhere there's a region where the initial conditions of the Big Bang were slightly different, leading to galaxies forming with different structures, stars evolving on different timescales, planets coalescing from different primordial compositions. Some of these variations would be hostile to life as we know it, creating universes where complexity never emerges beyond clouds of simple atoms. Others might be even more conducive to life, creating universes teeming with biological complexity on nearly every suitable world. All of these possibilities, every variation allowed by the laws of physics, exists somewhere in the infinite expanse beyond our horizon. The philosophical implications are staggering. If every possible version of you exists somewhere, what does that mean for identity, for free will, for the uniqueness of your experience? In an infinite universe, you are not unique. You exist infinitely many times, living infinitely many variations of your life. Does this diminish the importance of your choices, knowing that every possible alternative choice is also being made by some version of you somewhere in the infinite beyond? Or does it amplify the importance of your choices, because while other versions exist, they are not you, they are not having your experiences in your region of space? Some philosophers and physicists argue that this infinite duplication is uncomfortable but not fundamentally problematic. Yes, there are infinite copies of you, but they're causally disconnected. They can never interact with you, never communicate with you, never have any effect on your life. In a practical sense, they might as well not exist. Your experiences, your consciousness, your choices are happening here, in this region of space, and no duplicate, no matter how identical, changes that. The version of you, 10 to the power of 10, to the power of 115 meters away, is having their own experiences, equally real, but separate. You are not them, and they are not you. Others find this conclusion deeply troubling. It seems to suggest that nothing you do ultimately matters, because every possible outcome is occurring somewhere. Chose one path, and in another region of the infinite universe, another version of you chose differently. Every triumph, every tragedy, every moment of joy, and every moment of suffering, all of it happening infinitely many times across infinite space. From a cosmic perspective, nothing is unique, nothing is special. Everything that can happen does happen eternally throughout the infinite expanse. But perhaps the most mind-bending implication is what this says about the nature of reality itself. If every possible quantum outcome occurs somewhere in the infinite universe, then the universe is in some sense exploring the entire space of possibilities. Every potential path through the quantum landscape of possible states is being realized somewhere, somewhen. The universe isn't following one particular path through the space of possibilities. It's following all paths simultaneously across infinite space. This bears a strange resemblance to the many worlds interpretation of quantum mechanics, but manifested in infinite space rather than through quantum branching. The result is similar. All possibilities exist. All are real. All are happening. Now combine this with the eternal inflation multiverse. If our observable universe is one bubble in an infinite multiverse, and if each bubble is itself infinite, then we have infinity nested within infinity. Each bubble contains infinite space, with infinite repetitions of every possible configuration, and there are infinitely many bubbles, each potentially with different physical laws. The total space of existence becomes incomprehensibly vast, containing not just every possibility within our universe's physical laws, but every possibility within every set of physical laws that the landscape of string theory, or whatever fundamental theory governs reality, allows. Everything that can exist across all possible physics does exist somewhere in this nested infinity of bubble universes. Some physicists push this even further. If the many worlds interpretation of quantum mechanics is correct, then at every quantum event, reality branches into multiple worlds corresponding to different possible outcomes. Applied to cosmology, this would mean that every bubble universe is constantly branching at every quantum event within it, creating an ever-expanding tree of possibilities. The number of worlds would be not just infinite, but uncountably infinite, a larger infinity than the infinity of space or the infinity of bubble universes. Every possible quantum history of every possible bubble universe would exist as a real, physical branch of the universal wave function. At this point, we've moved from physics into territory that challenges the very meaning of existence. If everything possible exists, what does it mean to say something is real versus merely possible? What distinguishes the actual from the hypothetical if both exist equally in different regions of the infinite multiverse? These questions probe the limits of both physics and philosophy, regions where our concepts and language begin to break down, yet the mathematics is clear. Infinity plus finite complexity equals inevitable repetition. If the universe is infinite, duplicates exist. If eternal inflation is correct, bubble universes exist. If quantum mechanics generates many worlds, all quantum possibilities exist. The physics doesn't care about our philosophical discomfort. It makes predictions about the structure of reality, and those predictions lead to these mind-bending conclusions whether we like them or not. This might be the ultimate implication of what exists beyond the cosmic horizon, not just more space, not just other universes, but a reality so vast and complete that it contains every possibility, every variation, every potential arrangement of matter and energy that the laws of physics allow. Our observable universe, the tiny 93 billion light-year bubble we can see, is just one infinitesimal slice of this totality. Beyond our horizon lies everything. Every possible version of history, every possible outcome of every event, every possible universe with every possible physics. All of it real, all of it existing, all of it playing out in the infinite expanse that extends beyond the edge of what we can ever see. Stand outside tonight and look up at the stars. You're seeing a few thousand points of light, a tiny fraction of the observable universe. Billions of galaxies lie beyond what your eyes can see, but telescopes can reveal them. Yet, even those billions of galaxies are just the beginning. Beyond the cosmic horizon, beyond the reach of light, beyond the boundary of our observable bubble, space continues. It might continue forever, filled with infinite variations of everything you know. It might be punctuated by other bubble universes, each a separate reality with its own rules. It might unfold through higher dimensions you cannot perceive, or exist as quantum information encoded on distant boundaries. You will never see what's beyond that horizon. The laws of physics prevent it absolutely, but the evidence suggests it's there, vast and strange and possibly infinite. Everything you've ever seen exists inside a cosmic bubble 93 billion light-years across. But that bubble is not the universe. It's just the part the universe has shown you. The rest, the overwhelming majority of reality, remains forever beyond your view, knowable only through mathematics, theory, and the subtle signatures it might leave in the small portion of existence you can observe. If the universe is infinite, then everything that can exist already exists somewhere beyond the horizon, including another version of you, looking up at their own stars, wondering what lies beyond their cosmic edge, never knowing that you exist beyond theirs, equally real, equally unreachable, two instances of the same consciousness, separated by distances that make infinity seem intimate. The cosmic horizon isn't the edge of reality, it's the edge of the observable, and beyond it lies everything else. Everything possible, everything permitted by the laws of physics, everything that mathematics allows and infinity demands. We stand at the shore of a cosmic ocean whose far side we will never reach, whose depths we will never fully plumb, whose extent we can never directly measure. But we can see the waves lapping at our feet. We can study their patterns, decode their rhythms, and through careful analysis, infer something about the vast ocean that produced them. That's the work of cosmology at the frontier. Understanding the infinite by studying the finite. Knowing the unknowable by measuring its echoes. Seeing the invisible by observing its effects on what we can see, what exists outside the edge of the universe. If you're asking about the observable universe, the answer is clear. More universe. Space continues, matter continues, the cosmic web extends beyond our horizon. If you're asking about the universe as a whole, the answer becomes strange. There might be other bubble universes, there might be higher dimensions, there might be infinite repetitions of everything possible, or there might be something we haven't even imagined yet, something so far beyond our current physics that our best theories can't even conceive of it. The only certainty is that our cosmic bubble, our observable universe, is not all there is. It cannot be. The mathematics, the observations, the theories, all point towards something larger. Something we're embedded in but cannot fully see. Something that makes our entire observable universe, all 93 billion light-years of it, seem like a single grain of sand on an infinite beach. That's what exists beyond the edge. Everything. And we've only just begun to understand what that means.